my dear student, colleagues, and all the viewers who are watching this program from the Facebook page Physics Adda. I would like to invite you in my international webinar. So today it's our 37th physics webinar, and good afternoon to all here in Bangladesh, and good morning to all those who are watching from South Africa. So hope you are well and safe from Corona pandemic. And all we know that we're staying in a Corona pandemic situation, and as all the institutions have been shut down since March 2020 due to the Corona pandemic, so we can't continue our normal academic program inside the campus. So we have to start our online program. So you have already come to know that our Department of Physics, have already started some online program like online classes and online international physics webinar. So we are trying to adjust this new normal situation, and you have already came to know that we have arranged a series of webinars, and in those webinars, the physicists from different countries are coming as a main speaker, and they're sharing their experience with our student, and they are delivering their speech with our student, and they sharing their knowledge with our student. And I think by this way, our students are benefited. So the main aim of our program is to motivate and encourage our students in this Corona pandemic situation, and we do believe that this international webinar will help them to make interest in physics studies and research. And I'm happy to share with all you that it is our 37th international webinar, and this has happened successfully by due to all of your support, actually, and cooperation. And I'd like to say thanks all of you, those who helped me and encouraged me by arranging this webinar. And today it's very a great day for our department, because I'd like to welcome you all to a joint session between Pabna University of Science and Technology and University of Witwatersrand, Johannesburg, South Africa, in high energy physics. And we have with us here today Dr. Deepak sir. He's now working as Associate Professor, School of Physics, Faculty of Science, University of Witwatersrand, Johannesburg, South Africa, connecting with us from South Africa through online, and he has already connected with us. So, sir, welcome to our international webinar. And good afternoon and good morning in your country. So
hi, so it's great to be here, and thanks, Pretam, for organizing this. I mean, I completely agree that giving exposure to students from like people from different parts of the world speaking about their research and like their active research is great. So it's my pleasure, and I actually requested Pretam that I'll introduce myself. So who am I? Everything is fine,
it's
right?
My pleasure, actually, sir. It's my pleasure and privilege to host you, sir. Thank again,
you.
Sir. Okay, you can start.
And everyone can see my screen and myself and everything, right? Okay. So I actually am from Calcutta. I mean, that's like essentially your neighboring city in some sense. So I grew up there. I went to university there. So the picture on the right-hand side, that's where I did my bachelor's and master's. Then I went to Florida for PhD. So you see the picture on the left-hand side. That's actually a picture of a space shuttle launch, like a real space shuttle launch, which we saw from Kennedy Space Center. It was fantastic because we were actually, let's say, 10 kilometers away from the launch site. And this is, believe it or not, middle of the night, 3 a.m. And then we saw the whole thing light up. And then after a few seconds, we heard the sound. Now, as a physics students, you all know light travels faster than sound, but this was like a real demonstration of that. So I started working on Tevatron experiment, Tevatron collider in Pileup. When I was doing my PhD, I worked on City of Experiment. And then I finished my PhD. I moved to Dresden in Germany as a postdoc, and I moved to Atlas, which CERN, LHC was just starting off at CERN during that time. And then I spent a year in Geneva. Pretty much every experimental particle physicist do that. Then I did another postdoc in Glasgow, and from 2015 onward, I am working in Johannesburg, South Africa, in University of Witwatersrand. Now, I do have a connection to Bangladesh, apart from the fact that I speak Bangla. I don't know if anyone there is non-Bengali speaking, I mean, I don't know. I can switch to Bangla if the need arises, but I just want to make sure everyone understands Bangla. So Pretam, if you know what's going on, if you tell me, that's great. But it's fine either way. Yeah. So in 2014, there was a Bangladesh CERN School in Particle Physics organized by Professor Arshad Momen, among others. Some of you may have heard of him. And we had a bunch of international speakers. I mean, I'm considering myself international, although I was the only Bengali-speaking international speaker. And a lot of students, a lot of curious students from all over the Bangladesh actually took part. It's a pity that didn't continue. I mean, I think the excitement among the students was very overwhelming, and that was my first time in Bangladesh. So I loved being in Dhaka, like walking around, eating all the great food. So that was that, right? So now switching back to like more sciencey things, what do we do? I mean, I know you heard a talk by Professor John Ellis a few days back. I'm sure he explained many of these things, but I'm just going to like go in the slightly different route because I call myself an experimentalist. So we look at the actual data coming from the collider and try to make sense of it. So that's what I'm going to talk about. Now, what do? We look for needle in haystack. Literally, that's what we do. Because, and I'll explain why I'm saying that, but because we want to find new particles which never been observed, new elementary particles, but we have a huge background from other processes, so we have to like really work hard to find those, and that's why I'm saying needle in haystack. In fact, I can actually do even better and say like we are looking for broken pieces of needles in haystack, because we actually like for example this Higgs boson, which was discovered in 2012, which is this like huge moment for LHC. But Higgs, when it produced in a collision, and we'll explain that as we go along, you don't really get to see the Higgs in your detector. What you see is decay particles which originate from Higgs. So that's why I say it's looking for broken pieces of needle in the haystack is worse. Now, where do we do this thing? I mean, I'm sure you have seen pictures. We do it in Geneva, the French-Swiss border. We have this humongous particle collider underneath the ground. We have 4 points along this beam pipe where we bring the particles to collide with each other. How do we do it? We essentially use magnets. So think of optics, but rather than like mirrors and lenses, you have superconducting magnets, and they bend the beam so that at specific points in this ring, we collide beams going in either direction, and we have detectors, huge particle detectors. Let's switch back to a picture of a detector. Huge particle detectors surrounding the collision points. Everything that comes out gets detected in the detector. Now, we are not going to spend a lot of time on the detector, but think of it as like your very sophisticated digital camera, which takes a snapshot of everything coming out of the collision. Now, why do we do it? I mean, there must be a reason. We are spending like billions of taxpayer dollars to do this endeavor. Of course, I mean, there are two different things, right? One is you do it for scientific glory and to know more about nature. And so I want to classify this as like in this nice Venn, not really a Venn diagram, but this cartoon. The known is, of course, what we know. Fine, we all know like we have electrons and quarks, and this is known. This is known for years, decades. Then there is known unknown, and my favorite example is the Higgs. I mean, we kind of thought something like Higgs boson must exist from 1960s after Peter Higgs, Englert, and those collaborators, they came up with this whole electroasymmetry breaking thing. But we didn't discover the Higgs until 2012. So that was known unknown. We knew we were looking for the Higgs, and we found it. And we knew we needed something like Higgs to hold the standard model together. Whereas the unknown is the really interesting thing, because a lot of times in LHC, as we'll see, we search for specific new physics models. Like one of the most popular things, I'm sure Professor Ellis mentioned it, the supersymmetry, where every standard model particle is expected to have like a supersymmetric partner. So that would be classified as a known unknown if we find it. As of now, we haven't seen any sign for that. But there is this whole extra range of possibilities where we don't know what we are going to expect. But if we see it, we have seen something. And that's what is super exciting for us as scientists, that that we can find something in these experiments which we don't even expect. And that's for me is like the really exciting part. Of course, the other reason we do it is this is also something which trains people. I mean, trains students in data analysis, in electronics, in hardware. So these are all useful skills which our students get, and then they take it to academia or in industry, which is always very useful. So I would also say, like, these huge experiments, they are not just science endeavors, they're also like training and engineering endeavors in many ways. But anyway, so what happens when protons collide? This is a picture of a firework, but that's pretty much what happens. When two protons collide, you have a lot of particles coming out. Now, if I could do like a real, how do I say it? Real in-person thingy, I would probably ask for 2 volunteers and play a little game. But let's say we do this thought experiment, right? Because of course, virtually it's very hard to do. So let's assume I have 2 of you, and you have, let's say, ping pong balls. And you are facing each other, 2 of you, and throwing ping pong balls at each other. And let's say, like, 2 of you have like one ping pong ball in your hands, and you throw it at each other. The chances are, and you can like think of it, it would actually be very hard to hit, like make the ping pong balls collide. They would probably just pass through each other, pass like against each other and not going to collide. Now, if I give you, each of you, like now, I don't know, 10 ping pong balls, and you throw 10 ping pong balls at each other, then the chances are at least one of them would collide, maybe more than one would collide, right? I mean, this is something we can imagine. Now, that's what happens in IHC. If I just put one proton in my collider and I collide it, I mean, first of all, it will be hard to make it collide, even though, I mean, we have all these magnets and everything. I'm just keeping an eye on the time. But if you throw bunches of protons at each other, the chances are at least one of them would collide. So that's why we typically have bunches of protons, not just one proton, circulating in the things. And bunches actually contain like thousands, hundreds, thousands, and millions of protons. The other thing that happens when you throw bunches, inevitably more than one proton collide with another, and that results in something called pileup, which I'm going to come later. So what are the things we need to know? What comes out of the collision? And once we figure out what comes out of the collision, we need to know what processes actually create them, and what can we measure from them, and how does that tell us anything about nature. So this is a step-by-step process. Before going into that, let's just get some very basic concepts clear. And I believe you are physics students, so you have learned some amount of quantum mechanics. So everything is quantum mechanical in elementary particles domain. So outcome of collisions are probabilistic. And this is something which is slightly disconcerting, but there are no exhaustive list of possibilities. Because if there were, then we would not be doing this. If I knew my collisions can give me 20 possible outcomes, then we know everything. But we are hoping there would be a 21st possible outcome, maybe with a very, very small probability, or definitely with a very small probability, because otherwise we have seen it, but that must be there. So that's why I would say there is no exhaustive list of possibilities. We know what are the processes our standard model predicts. And then we use this funny term called cross-section. So how often a particular process occurs is given by cross-section. This is and if you read any particle physics paper, if you hear any talk, people will be like, oh, cross-section for Higgs production is so small. That essentially means probability of producing Higgs is very small. Now, how does the collisions occur? I mean, of course, protons are not fundamental particles. They have quarks and gluons inside them. And when you move protons at a very high speed, if you have done some special relativity, they kind of appear elongated. So essentially you have an overlap, but remember, protons are kind of hollow in some sense. So in order to have a interesting high energy collision, you must have, this is a very overblown schematic diagram, but you must have one quark or gluon, we collectively call them partons, overlap with another parton from the second proton. That's the only way the collision would happen. If, for example, you see the red and the blue one at the center are overlapping, so you have a collision, but that's pretty much it. You don't have a second collision here. Now, coming back to that, we really don't get what is coming out of the collisions, because whatever is produced right at the collision, those particles, most of those particles decay into other things. Specifically, the interesting particles like the new heavy particles or the Higgs boson, they decay into other particles because of their finite lifetime, and so they decay before they reach the detector. So what we get in our detectors is the decay products. And the detectors also are machines, right? So you do your undergraduate or postgraduate labs, and oftentimes you don't get the result you expect. I mean, if you measure small g and you get 9.81, I'm sure your lecturers would be very, very worried that what's happening. So things don't work. I mean, things have, because they're instruments, and no matter how hard we try, no matter how hard the world's best minds try, we still have detectors giving us slightly different readings, slightly inaccurate readings, or missing some particles. So we have to account for all of that when we try to do physics. So that's the detector. So in this picture, you would have the protons coming from either side, colliding right at the center, and then the detector is kind of like cylinders around that point, so that everything that comes out in the transverse direction, so XY direction is where we measure everything, Z is the direction where protons are coming in. And we can't measure anything in the Z direction because we have to have the opening, right? Otherwise, protons can't come in. The detector, as I said, we have different layers, different concentric cylindrical layers, and different layers measure different things. So the closest part, what we call the tracking detector, is where we have like a gaseous or some kind of very thin liquid medium, where when charged particles pass through the medium, and we have a magnetic field there. So when charged particles pass through that, they bend, electromagnetism 101. And from the curvature, you can determine the momentum and the charge, right? That's what you have done from your second year or first year. So that's what we use. Very simple physics principle. Then the second layer is called electromagnetic calorimeter, where electrons and photons, these are lighter particles, they are stopped. And they deposit all the energy. From the energy, you can see what was the energy of the particle that came in. Also for electrons, you can match the energy deposit with the tracks. For photons, of course, it's not charged particle, there are no tracks. The second part, the blue part in my diagram, is what we call hadronic calorimeter. So hadrons are heavier particles like pions and kaons and all these elementary particles. So the hadronic calorimeter is built with the material so that these hadrons are stopped and they deposit all the energies. So that's what we get, those things. Some of them would have tracks, some of them won't. And then finally, the outermost layer is muon spectrometer. Muons are the heaviest among these particles, so they travel the most before getting stopped. So we have like a separate detector just outside to get the muons, and there we measure muons. So this is what we measure. Now there is, so yeah, this is kind of a, okay, I'll come back to that picture later. So these are the things we measure. And then there is something else we measure, because I have not talked about quarks and gluons. But when quarks and gluons collide, you have a lot of quarks and gluons coming out. Now, you may have heard that you can't get free quarks and gluons in nature. You just can't because of quantum chromodynamics. They have their strong interaction. So they always form these mysterious hadrons, which would have no color charge, where quarks and gluons are assumed to have color charge. So these are the hadrons you get in the hadronic calorimeter. Now, typically, a bunch of hadrons, like if you see in the picture, like the red wiggly line at the top of the cone or at the bottom of the cone is a gluon, which probably came from the collision. And then you have this whole structure, which you call parton shower. Gluons split into Q bar pair, quarks emit gluons, gluons further split into Q bar pair. You have this whole structure, which we call a shower, this cascade, which we call a shower, and eventually the shower ends up forming colorless hadrons. And what we want to do is we want to make sure we can work with the initial gluon. Of course, we can't, because that's not something you get. But if you collect everything that came from the decay of that gluon in a conical object, I'm going to switch to a Bengali term now. Sorry if they're non-grammatical. Think of like a jhalmurid thonga. You collect everything that's coming out of one gluon in that jhalmurid thonga, and that's what I call a jet. It's a 3D object. That's why your thonga is a very good analogy. And so every particle that coming from the decay of the quark or the gluon would be collected in this jet. And so jets are our fundamental objects, and they are proxy for quarks and gluons. So rather than doing with a bunch of hadrons, we just make them in a jet and we add all their momentum and collect them in one object. So that's what we do. And there is something else which we don't measure, which is what we call missing energy or missing transverse momentum. Now, what are these? If you have a particle which do not interact with the detector, but which is produced, for example, neutrino, which is the only standard model particle which do not interact with the detector, then what happens? You have your standard energy momentum conservation, right? You all know that from like your high school, probably. That if you have n number of particles produced, if add all their energy and momentum, they should add up to 0 if you do it factorially. Now, if you have a neutrino which doesn't interact with the detector, it won't add up to 0. It can't. Sorry, is there a question? Okay, so it can't. So you would have an imbalance of energy momentum in the detector from the stuff you measured. That is what we call missing energy or missing transverse momentum, and that signifies a neutrino. But that can also signify new particles which do not interact with the detector. For example, dark matter particles. By definition, they're dark, so they should not interact. But so far, all the missing energy signatures we saw in the detector are consistent with neutrinos, unfortunately. If not, then we'd be very excited. So these are the objects. And now let me go back to my grand picture. So this is like a schematic diagram of how everything happens. And there are quite a few components. I'll try to spend like a few minutes on that. So the two gray circles on the either side are my protons. They have quarks and gluons. Let's say one quark from each collide in the star, which is marked as HS, or the hard scatter. And let's say a Z boson and another quark come out of that collision. Like that's a very standard collision. The Z boson is denoted by the light green arrow at the bottom. Sorry, and the light green circle. And a Z boson again have various decay modes, but it decays in E plus E minus, mu plus mu minus, all of this. So let's assume it decays into E plus E minus. And since electrons are charged particles, they can also radiate photons, Bremsstrahlung, again, which you probably know. So we have a photon coming. So that's one part. Leptons are simpler. They only radiate photons, and that's it. Is everything okay?
Yeah. No problem.
Okay. No, that's fine. All right. And then the red, our red quark on the top, which is where a lot of these things happen. So the whole pattern shower I described, that would happen from this quark. So the gluons, the blue gluons are getting emitted, and all of these things are happening. And also, because quarks and gluons are charged, they can also emit photons, and they finally form hadrons. So this is one part. But remember, we also have other quarks and gluons in both protons. So they can also interact, which we call double parton scattering, or in general multiple parton scattering, because they're there, they should do something. And the ones which do not actually interact from another quark or gluon, they're still there, but they can't live there forever. So they also need to form hadrons. So they have their mini parton shower, and the DPS, double parton scattering, it would also have its mini parton shower. So, and eventually what you get in the detector is a mixture of everything. I mean, when I draw this diagram, theoretically, I can separate out every component with different colors. It looks nice. But when you actually get in the detector, you just get a bunch of hadrons, electrons, muons, photons, and then you have to kind of do a puzzle solving where you have to try to estimate what came from what, if you can at all. So this is a picture of a real collision event. You can see like there are jets going in 4 directions. So this event with lots of jets, and it's, as you see, it's very energetic events. And the name jet came from this huge water fountain in Lake Geneva, which is 20 minutes from CERN. And this thing is in French. It was called Jet d'eau. U stands for water in French. And from that, I mean, that's the folklore that we use the name jet. So this is the original jet. From that, we named our particle physics objects as jets. Now, I said there are Pileup. Now, I did talk about when you're calculating missing energy, you need to do conservation of energy momentum, and sure. But now what happens if you have multiple protons colliding in the same collision, and the detector sees objects coming out of both the collisions, or 30 of these collisions? So then the thing becomes very messy. And now, of course, we don't have the time or scope here to go into the details, but I just wanted to point out Pileup, which is the name for this thing, is one of the things which we have to deal with. We found ways to limit contributions from Pileup or identify contributions Pileup and get rid of them so that we get a clean single scattering. But it's never easy. We never really get that very cleanly. So that's one of the problems at the LHC. I mean, we always have to deal with Pileup whenever we are doing these things. The other thing I would describe before I go into like how we make sense of data is something called trigger. Again, this is a whole lecture by itself, so I'm not going to go into that. But the idea is when you're colliding protons and protons, and the time between two collisions is 25 nanoseconds, so that's like 40,000 collisions per second, if I'm not mistaken. That's a lot. So your detector has to process these things, and then electronics, basically, like detector and the connection, and it's basically electronics. I mean, I'm not an electronics person. And then you have to save the whole data in some kind of storage. It turns out that it becomes overwhelming for any electronic system to store that much of data coming in a single second. The electronics get overwhelmed, the storage gets overwhelmed. But that's also fine because nature is very kind and boring. So most of the collisions actually do not result in very high energy exchange. Nature is lazy. It doesn't want to produce heavy energetic particles in all the collisions. It only does it like 1 in a million. So we have to be smart, and we have like the collisions where there is nothing exciting going on. Why do we need to process it? Why do we need to store it? That's just wastage of resources. So we use something called trigger, which is also like an electronic implementation, which essentially says, oh, is there a certain amount of energy exchange, energy deposit in the detector? If not, let's not set this event. I mean, I'm oversimplifying it, but that's what trigger does. It just very quickly tries to identify, is there something interesting going on? If not, throw away the event. And we throw away most of our events. And we try to set the events which are potentially interesting for physics. There is another component which we have to mention before we talk about the whole analysis process, because we can't try to see if there is new physics in data without knowing what the current physics is telling us, right? Because you need to have a baseline. And if there is something over the baseline, then we'd get excited. Oh, there is new physics. But what decides the baseline? We have to know what decides the baseline. The baseline is decided by simulation. So we have simulation programs, which is an industry by itself, which tries to simulate events which are realistic, faithful reproduction of what LHC would give us, but only of the known processes, the processes which have been measured by which have been like predicted by standard model, measured with unprecedented accuracy and all of those things. Now, if you have done any field theory or that, then you would know like everything in standard model is calculable in terms of like summing up the amplitudes of Feynman diagrams and everything, but let's not go into that. What I want to say is like the event generators have like two distinct parts. One is a matrix element calculation. Essentially, it's a probability amplitude calculation. and then some part which is very low energy, so that is actually not calculable in a parametric expansion. So we kind of model it, and we kind of model it in the programs and try to. Okay, I'll come to that. Now, these simulation programs are typically called Monte Carlo programs. Monte Carlo is a French gambling town, and why is the connection? What is the connection with gambling with particle physics? Because essentially we are looking at a large number of particles. As we know, quantum mechanics means amplitude probabilities, but event generator essentially tries to like match the probability distribution which nature would give. So in that sense, and it generates like every single collision, and every single collision has to have like different particles produced with different energies. I mean, it has to be realistic. So these generators, of course, have a lot of physics in them to make it realistic. It has to obey all the conservation principles, but then it also has to have a spread which nature would give us. So that's why they are called Monte Carlo. So yeah, you have to assign a lot of random variables essentially. Now, how do you do this Monte Carlo? I thought we would have a very quick example. So Monte Carlo is a method of integrating using random numbers. So let's say we want to find the area of a circle, and we have this rectangle and a circle. Now, if you like close your eyes and throw darts, or let's say just throw, I don't know, stones in this whole thing, and whenever the stone hits any part of this thing, it makes a mark. If you throw enough stones to cover the whole thing, then you can say, oh, I know how to get the area, and you know how to get the area of a square, but you don't know how to get the area of a circle. Maybe you never heard of pi r squared. Then what you can say, if I take the ratio of number of darts or number of stones which hit the whole thing, and I take the number of stones which hit inside the circle, I take the ratio, then you get the ratio of the circle within some approximation. The more stones you throw, the approximation will be better. So that's what Monte Carlo event generators are. The more events you generate, you are closer to how nature behaves, if your program is right. And these programs have some what we call tunable parameters, because as I said, part of it is ad hoc modeling. So this ad hoc modeling must reproduce data. So what we do is we have this defined phenomenological parameters which we kind of tune, looking at data, looking at specific data distributions, and try to get it. And I want to mention it because this is something I have worked on for a long time. In fact, the tunes Atlas uses is something I was very involved in. Anyway, so now in the last 20 minutes or so, I'm going to talk about the actual measurements and searches we do in the LHC. And analysis is a procedure by which we extract the physics information from data using a lot of simulation, as we will see. Measurements are designed to verify standard models. So if standard model says the number of Z boson should be this, or the transverse momentum of Z boson should follow this kind of behavior, that's what we want to check. Or we want to measure the top quark mass, that's what measurements are. And the searches are designed to look for beyond the signatures. Now, why do you do measurements? Because you might claim, oh, LHC, we are trying to find new physics. Sure, we are. But also, standard model processes have pretty much background to every potential new physics process. So you need to understand your background very well, and you have to actually implement it in the generator. So unless you measure things very well, your generator should not, of course, reproduce it. We want to also measure the free parameters of standard model, like top quark mass, Z mass, W mass, because it's fun. And then we want to make sure the generators are doing well. So we measure things and we compare the generator predictions. And if the generator prediction doesn't match up, we work a bit on the generator to make sure it matches up with the data measurement. And as I said, these are background for searches. Now, of course, again, search is like a huge industry, but just to kind of give you an idea, most of the standard model processes have a very, how do I say it, very smooth shape. So if you measure, let's say you take the jets. We talked about jets, which are coming from quarks and gluons. Let's say you are looking at two jets and form the invariant mass. If this is coming from pure QQ bar to QQ bar, then you would not see any structure. This would be the steeply falling line. As I said, nature is lazy. So as you go higher in mass, you get less. And so y-axis is cross-section, means number of events. X-axis is mass, which is this invariant mass I formed. Now higher in mass we go, you see the number decreases. Because nature is lazy, it doesn't want to produce too many high energy events. But it's a steeply falling smooth distribution. Typically, these are in log scale. However, if your two jets are coming from a new physics, new particle X, a heavy particle with a specific mass, then if you form the invariant mass, you would have a bump at the value X, like this light blue thing. So that would be a signal. You have many more events there compared to standard model because I have this new X particle which is decaying into two jets. So this is what we typically call resonance search in, and an overwhelming fraction of the searches at the LHC are resonance search looking for bumps. Sometimes it's not so clear, so you just try to find if there are more events in coming from certain processes, what we call cut and count. If you have an excess of missing energy, which you haven't found, that might indicate dark matter, blah, blah, blah. The searches, and you might ask, and I would ask if someone tells this to you, but how do you know what you are looking for? So we have, again, very broadly two categories. One is what we call theoretical model driven. So supersymmetry, which I'm sure someone mentioned, you have models which says, oh, there is extra dimension. The universe is maybe, I don't know, 6 dimensions, but we don't see 2 of the dimensions because they're too small. Don't confuse this with string theory. I mean, that's a different ballgame. I'm not going there. There are models which says there are these tiny quantum black holes which are completely harmless, which are not going to eat us up, but maybe they'll decay into a lot of jets. There are models which predict massive neutrinos. As you may know, neutrinos are particles with very tiny mass, but there are models which have massive neutrinos. Some of them may be dark matter particles, candidates, whatever. So these are like essentially theorists sit down and write a very nice, elegant mathematical model, and they say, oh, the signature of this model must be this, search for it. And then there is a more of a second kind, and the distinction is sometimes blurry, but the idea is it's more what we call model driven. I mean, if we look at 2 jets and we form the invariant mass, just as I was saying, would we see something? If we look at 2 electrons and form the invariant mass, of course, we would get peaks corresponding to Z boson where there is E plus E minus, but do we get a peak in some other place? And these are kind of like signature driven. So dark matter particles, are there like a 4th generation of quarks or leptons? Are there this composite leptoquarks, which is these hypothetical leptons and quarks? Do we have a heavy partner of W or a Z boson, which have every property like that, but at the TeV scale rather than at hundreds of GeVs? Are there particles which were called lepton flavor violating? So typically we know any reaction should be lepton flavor conserving. You can't have a particle X decaying into E and mu, but do they exist? We look for them. And then there is this thing which is becoming very popular nowadays called LLPs, which are like long-lived particles. So means maybe there is a hypothetical new particle, but it is very long-lived. So it doesn't detect, as I said, inside the detector. Maybe it detects like halfway down the detector, or maybe it decays completely out of the detector. Maybe it decays under the Geneva lake. Who knows? So people have built such models, and people are trying to build even new experiments to search for these things. So this is kind of a picture of the LLPs. Of course, this is assuming everything at least decays partly inside the detector. So yeah, I mean, I can have these slides available to you via Pretam later. That's easy. Now, okay, so now we're at a stage. We have simulations. We know what we expect from standard model. We know our objects. We know what we are looking for. So from this, we need to form observables. A very simple example was the invariant mass, but there are quite a bunch of them which would be sensitive to these new physics signatures. And cross-section, now that we have kind of learned all of these things, the number of events, this is what eventually we want to get. This is given by what we call luminosity. That is essentially the number of collisions that happened at the LHC times what we call theoretical cross-section for that process. So this is a number we get from standard model, like we expect so many Higgs bosons to be produced if there are so many collisions. Then there are two terms called efficiency and acceptance, which are essentially experimental quantities. Because detector is finite, you might have particles getting produced but not being caught in the detector. And efficiency is maybe there are particles produced but you don't measure their full energy, or even there is detector but you still miss it. So we have to account for those things. And so let's say this is corresponding to some signal, but what you actually measure, you measure the total number of events. Events don't come with label that I'm from a new physics process and I'm from background. So you measure everything. So the left term is the signal plus background. So that's the total number of events we get for a process. That's that. From that, you can calculate the theoretical cross-section if you don't know it. Now, as I said, the analysis is essentially how we extract physics. A particular signal has a specific final state. We'll have some examples very shortly. Other standard model processes can produce a very same or similar final state, which would be called background. And then the whole game becomes identifying signal over background. And how do we do that? We do it by what we call object and event selection. We require certain thresholds for different energy momentum of the objects. We require certain angle between the objects, which would be consistent for that signal. And hopefully that would reduce some of the background. And then we use this formula S over square root of B, which is called the significance. And that significance tells us like if we can actually find that signal. So because I'm in South Africa, I have to show this by contract. So you have like a lot of background, and then you apply your cuts, apply your requirements, and maybe you get some nice new signal. So there are different types of backgrounds, and we have names for them. Irreducible is what we call the exact same final state coming from a standard model process compared to the signal. Reducible is, it's not the exact same final state, but because of misidentification in the detector, for example, we often misidentify electrons as jets and jets as electrons because they all correspond to energy deposits in the calorimeter. So even if your signal is E plus E minus, E plus jet final state might look like that because maybe you misidentified the jet as electron. And then, okay, let me not go into the combinatorial thing because that would be too complicated. So apply selection cuts on the objects and event topology to maximize signal and minimize background. But, and this is a huge but, you don't want to bias yourself. Because as physicists, as humans, we all have our biases. And there is no way you can get rid of them. I mean, some of us are very cynical, so we are like, no, we are never going to find new physics. It's just hopeless. And some of us are very optimistic. We are like, we are always thinking there is some new physics hiding under that. Now, these are all human biases. We don't want to do our selection cuts with our bias to enhance the actual signal. So what we do is, when we do a search, we typically divide our events into two classes, at least in two classes. One is called signal region, where we expect this new physics signal you are searching for. And then we essentially what we call invert a cut. So we look at an orthogonal region, which roughly is the same as the signal region, but have one orthogonal characteristic. So let's say we are looking at a new physics where the mass, invariant mass, would be, let's say, between 2 TeV and 3 TeV. But we say, okay, fine. But we would not look into that. We would call that the signal region. We would only look at 1 to 2 TeV first, and that would be my control region. And then there I would see if my background is modeled well by simulation, all of that, and would blind our signal region. We would not look at data. We would only look at simulation. Only when we are confident that in the orthogonal control region, my simulation describes the data. And in the control region, you don't expect new physics, so you expect your background to be all coming from standard model process. So if you consider all the contributing standard model process in simulation, you should be able to reproduce the data. There should be very good agreement, and typically we get that. And then once you're happy, we are like, okay, we understand this thing. We understand that the invariant mass of standard models is given well by the simulation. Then we open the box, unblind it, and see if indeed we have more data events than we expect coming from the background. Okay, I still have. Okay, so I'll quickly go through this. So Higgs boson, since this was like the big discovery, a few years, not a few, now it's like 8 years back. So first, we looked at Higgs boson production modes, and we didn't know it was 125. So let's focus on the decay modes. So the three most important channels, or three most important decay modes of the Higgs boson we looked at in 2012 was Higgs to 2 photons, Higgs to 4 leptons via 2 Z bosons, and 2 leptons and 2 neutrinos via 2 W bosons. And in each of these cases, we identified the final state, we identified the background, we tried to figure out how to estimate the background, how we get read of most of the background, and we found it. Again, I'm not going to go too much in technical details, but what I'm going to show you is this diagram. So hopefully it works, and I'll let it run and I'll explain. So what happens is, this is an animation where the blue line is the background, which is standard model. So if no Higgs existed, data should be completely consistent with that. However, if there was a new particle, namely the Higgs boson with a mass of 125 GeV, then you would have excess of events. This is the diphoton invariant mass around 125 GeV. So, and this plot essentially shows how we, and this is running again, how like we are collecting more and more data, and you can see like initially it starts off being very similar to standard model, and then you kind of see the slight excess building up around 125, and you see this bump around 125, so that corresponded to Higgs because that was clearly over standard model prediction. We'll do one more for the Higgs to ZZ to 4 lepton. Again, it's the same story. You would see the red is the background, the black points are data, and they're building up. And first you see there is a peak corresponding to Z boson masses. But then you see there is also a peak building up at 125, where the Higgs is. So as we collect more and more data, the peak becomes more pronounced. The statistical uncertainty on the data decreases slightly, and you get a nice Higgs boson peak. Now, of course, we looked at different decay modes and combined all of them to get the Higgs. And in high energy physics, the significance, which I mentioned before, requires our significance to be greater than 5 in order for us to confirm a discovery. What does it mean in everyday terms? If we could perform the experiment 3.5 million times, of course, we only have one experiment, so that's that. Then only once the background fluctuation, because quantum mechanics tells us everything that could happen can happen, but only in 1 in 3.5 million times, the background fluctuation would give rise to that peaks you saw. So we are fairly confident that this is the Higgs boson. It's a significant deviation from the background. Of course, combining every channel, and combining every channel means you have to combine the systematic uncertainties, all of that. So it's not a very trivial job, but that's what people did. Now, of course, we found the particle. How did we know it's the Higgs boson? We had to measure the properties. We measured the mass. The mass was eventually close to 125. Signal strength is like how many Higgs bosons you expected from standard model, assuming now the standard model has Higgs boson, and how many you got. If the number is close to 1, everything is good. It turned out mostly close to 1. So that was that. Now, that's 2012, right? So you might ask, okay, that's like 8 years. What have you up to now? Unfortunately, we didn't find new physics. We measured different standard model processes at very high accuracy, and I'm very proud of that achievement because we had to come up with new techniques and stuff, but we measured things. We improved the simulations based on our measurements. We have done that. We have searched for many, many new physics signatures. I mean, the list I presented was not even like 1/10 of that. But unfortunately, without any luck. But then again, I mean, I know this is an era of instant gratification, but things take time in science. In Tevatron, it found, if I'm not completely mistaken, we found the top quark 12, 13 years after the experiment started. I mean, LHC were lucky, we found Higgs within 2. But maybe we are in for a long haul, and that's absolutely fine. I mean, that's how science progresses. And also, we have excluded many new physics possibilities. A null result is also an interesting result. We can say like W or Z prime bosons doesn't exist until few TeVs. Leptoquarks doesn't exist until few TeVs. I mean, we have done we have explored a lot of new physics models. But because we are always impatient and we want to do something innovative, the focus has shifted more on what we call unusual topologies, like jets, but jets not containing hadrons, but containing electrons. I mean, all sorts of things, and we are looking for those. Also, there is this huge era of machine learning, which I don't have the time to go into, but the whole idea is you allow computer algorithms to figure out which events have slightly different characteristics, and computers are not biased. So, and we use these machine learning methods to discriminate signal against backgrounds in many cases, and it's something which has really taken over the field in the last couple of years. Right. So I always try to end with this slide because this is something which I think keeps us humble. So 10 years back, 2011, almost 10 years back, I went to a conference, and David Grosso, who is a very well-known physicist, had 10 predictions which he thought would happen in 10 years. And let's see where we stand. QCD tests and applications will greatly improve higher order calculations, theory of fragmentation heterogeneity. Fragmentation heterogeneity is the process by which we form colorless hadrons from the colored quarks and gluons. I would say yes. I mean, I would say 50% yes. We have NLO higher order calculations for many processes. We still don't have a theory of fragmentation heterogeneity, but I think we are getting closer, and we have very well understood models. Atlas and CMS would discover Higgs boson. No comments needed. Unfortunately, no evidence for SUSY particles, so that's a no. Plans will be underway to build a linear collider at CERN. And US, forget US, but people are talking about new colliders in China, in Japan. So I think this is also yes. No direct detection of dark matter wind, unfortunately. Alice has seen quark gluon plasma, yes. I think we have discovered some Z mesons, maybe in LHCb. We have seen gravitational waves. String theory is still a theory. It's very much a mathematical conjecture. And we still don't understand why QCD coupling constant is so small. But I think we are like halfway there, which is always great. Now I'll end with a blatant self-promotion. Last year, was it last year? Yeah, it was last year. I ended up writing a book on experimental particle physics based on the course I teach here. But it's not like a textbook. It's more of an introduction to our field. Everything I talked about can be found in that book, and much more. It's like a 260 page or whatever. Now, Google it if you find it. Great. I know you guys are very resourceful. If you can't absolutely find it and it's asking you for money, then send me a message or send me an email or ask Pretam to get in touch with me. That might be better because I don't want hundreds of Facebook messages. I can't deal with that. Sorry. I can send him like a private link. I'm technically not supposed to distribute it because everyone is supposed to buy from the official link. But I don't care if it helps some students to get excited about our field. I think that's a good enough reward. So yeah. So I think that's all I have. I will minimize my screen or minimize my thing so that I can at least see what's going on in the chat. So thank you.
So thanks, sir, for your wonderful session. It's a very great webinar. I think students have learned a lot of things. So in your slide, a lot of information, experimental information is CERN. So I think it will be very helpful for our students. So if you allow, we can start our discussion. So I have got already one question. So I have added the question in the...
Right. What is the actual theory for relationship between measurements referring to microparticle and field waves? Right. I'm not a theorist, so I'll give you a very experimentalist answer, right? So we measure particles, things which hit the detector, or things we don't hit the detector, like missing energy. Now, if you have a field, for example, the Higgs field, which is the obvious example, that has excitations, the excitation of the Higgs field produces these particles known as Higgs bosons. And then we measure the decay product of the Higgs boson, and we confirm that's the Higgs boson. So of course, we can't really measure, what do I say, the fields. I mean, that's not something you can do. Excitation of fields which manifest themselves as particles or something which we can see in the detector, that's all we can measure. And then it's like puzzle solving. Whatever you have measured, where it is coming from? Is it coming from something you already know, or is it coming from a new field? Who knows?
Yes, so thank you, sir. So one question in the inbox: what is quark-gluon plasma?
Okay, so again, this is not the area of my expertise, but I'll try to explain. So quark-gluon plasma is kind of thought of as the fourth state of matter in some sense. It's a state which has extremely high temperature, and quarks and gluons, which are the fundamental particles in QCD, they kind of fuse together to form like a state of matter. That's essentially what it is. Now, Alice experiment looks for that, and they have claimed that they can see the existence of this kind of very high energy quark-gluon plasma. But yeah, I mean, again, yeah. Typically, that's not something we do in Atlas or CMS. Our focus is more on discovering high energy or high mass particles.
Okay. So thank you, sir. There is another question. What will be the problem if a large energetic particle produced by the particle collision?
It's not a problem. It's great. That's what we want. That's exactly what we want. I mean, of course, as I said, nature is lazy. It doesn't give us very high energy particles very often. But those are the events we're interested in, because whenever you see a very high energy particle, you always wonder, did it come from standard model, or did it come from some new process? So that's exactly what you're looking for.
So thank you, sir. I think a student will ask the question later also, as the video will stay in the Facebook group and YouTube. So I can send you the question later. And
yeah, if you send me the YouTube link, and if there are questions on the YouTube comment, I'll be very happy to answer.
Yeah.
Now, one of the things I want to mention,
okay.
I am very accessible. I mean, if you want to discuss any work-related stuff with me,
of course, we will definitely discuss.
Yeah. I mean, I'm very happy to do that, but I want to give a disclaimer, because this happens every time I talk to people. Please don't flood my Facebook, because that's typically.
I understand.
No, I mean, I know you understand, but I mean, a lot of times students get very excited, and I get like 50 friend requests and 100 messages. Please don't do it. If you want to discuss physics, put in that effort. My email is everywhere online. I mean, Pretam find it, so I'm sure it's easily findable. Find my email, or you can send it to them. Send me an email. Send me an email. I'll reply as soon as I can. Try to help you. And then if we like discuss a lot over email, I feel like I want to add you on Facebook, we'll do it. But please don't start adding me on Facebook, because I don't want my real like friends who I actually talk to get hidden under. So I mean, this is I just want to make sure. I mean, I don't want to sound rude. I mean, I'm happy to have conversation with students. I mean, from that particular school I mentioned in Dhaka, few students contacted me. One of the students actually did like a virtual online project with me, and then I'm not going to give you the name because I'm sure I didn't ask her. But she then did a PhD in France. So I mean, I'm happy to help and like mentor students, but please, I mean, respect my privacy.
Thank you, sir. So I think they will understood this, and if somebody want to actually apply for masters and PhD, what are the opportunity for Bangladeshi student in your university?
It's very difficult. It's very difficult because we typically they are very reluctant to fund non-South Africans. There are some external fundings which we can explore once sometimes we get it. But again, I mean, if an individual student approaches me, I can talk with him or her and try to see what the best option for him or her, maybe.
Yeah. Okay, so thank you for your kind presentation and your nice, actually, suggestion about everything. So hopefully, this presentation will help our students, those who are studying in particle physics and nuclear physics. They must be actually benefited by this lecture. And I'm definitely sure that you have also enjoyed to talk with us also, as you are
I have.
Bengali. So, yeah. So we're pleased, and I'd like to say thanks on the behalf of the Department of Physics, Pabna University of Pabna University of Science and Technology. And so we actually very glad actually that you accepted our invitation. So our university is far from Dhaka, but still we are trying to organize some international stuff. And today it's our 37th, and our Department of Physics, Pabna University of Science and Technology, feel proud actually to host this type of program. And scientists like you actually accepted our invitation and delivering your speech with our student. That actually encourage us and encourage our student also. I hope this will help them to feel interest in physics. So as we actually the main aim to encourage and to feel interest in physics. So we have to encourage the next generation actually. So
Absolutely,
those
absolutely.
yeah.
No, that's why I
And
like talking to young kids, because
yeah,
I mean the possibilities are endless if they get aware of. I mean, not just my research, as you said, you're organizing this for like last few months. So
yeah,
I'm sure they are hearing about many things, and different people would be interested in different things. That's what I tell my
yeah,
students. Like some of you would like particle physics, but some of you would also hear this and realize this is not what you want to do, and that's also something you learned. That okay, this
yeah,
is
yeah.
not I feel like doing. I might feel like doing atmospheric physics, and that's great.
And though we are suffering from a very bad or passing a very bad time, but I think this makes a new opportunity for like this online session, like international webinar and other program. Actually, they may present like international professor with with this online stuff. So I think so we actually try. I don't know how it will work for them, but we'll try our best that if anybody actually will benefited by this program, that will be very actually encouraging
No,
for us. And
absolutely, absolutely. But I mean,
and for that actually I am very grateful to you people, those who are accepted my invitation.
no, but I also think that's for you. I mean, I understand you are far from Dhaka, not far. I don't know the map very well, but not
Yeah,
close to Dhaka.
yeah,
And probably I understand it's a relatively new university,
yeah,
and
yeah, of course.
where you are taking such effort, and you really care about students, because clearly you are doing this for all the students who are like, we want them not to like feel cut off from the whole university and the research
Mhm.
field. So I think I really applaud you for doing this, because I mean you clearly sense there's an opportunity. You took initiative. I mean, of course, I realize it's a lot of work. You have to send emails and then
Yeah.
coordinate. I mean, so yeah. I also thank you for like putting in that effort, because not
Yeah.
everyone is doing that.
Thank you, sir. So, if you allow me and if you give me time, next time I will arrange a webinar with Bangla. So, as you are Bengali, so I think the mother tongue will help them to understand more.
I mean, I
So
was
next
not
time,
sure I would switch to Bengali, because I mean, I think I felt there are people who would not understand. I mean, I didn't
I
want
think
to.
they understood, but hopefully, if you allow, then we can.
I mean, I can't. I don't think I can explain all the terms in Bangla, because the terms like jet
Yeah,
is a jet is a jet, work is at
yeah,
work. But as I said, I mean, I gave an analogy that with the jalmuri tonga. I mean, আমি বাংলায় কিছু কিছু কনসেপ্ট বোঝাতে হয়তো সোজাভাবে পারবো।
না ঠিক আছে। তো আপনাকে অনেক ধন্যবাদ। লাস্টে একটু বাংলায় আই জাস্ট ওয়ান্ট টু সে ইন বেঙ্গলি অ্যাজ সো আপনাকে অনেক ধন্যবাদ যে আপনি অনেক ব্যস্ততার মধ্যেও আমাদেরকে সময় দিয়েছেন। তো সেজন্য বাংলায় বললাম, বাংলা বলার একটু সুযোগ নিলাম। সো থ্যাঙ্কস এগেইন স্যার for
খুব ভালো
accepting
লাগলো।
our invitation, and hopefully we will arrange another webinar with our student. And as this video is keep in my Facebook page and YouTube. So if anybody asks question, I will discuss with you again. So thanks,
No,
sir.
no, I'll keep an eye on this. And as I said, I'm very happy to get emails from the students, and like because everyone has different questions and different things. So I'm happy to do that. All right, take care then.
Okay, bye, sir. See you.
Bye-bye.